Hello, and welcome to this problem-solving video on a particle in a box. So, in this question, we're going to be really dealing with the fact that when you start putting particles inside boxes and confining them into certain regions of space, quantum mechanics has this nice result that they cannot actually be at rest. The more you confine them, the faster they have to move. And so we're just going to explore that in the context of particular proton that we're going to place in a cubical box that has side length of 10 to the negative 14th meters. That distance is actually 10 times the size of an atomic nucleus, so that's why we've picked it. And we just want to know that according to quantum mechanics, in order to confine and know that this proton is really in the box, how fast does the proton have to be moving? So let's look at it. The fundamental thing that gives us this seemingly weird result of the fact that you can't actually be at rest in a box is Heisenberg's uncertainty principle. And so that is this form delta x, delta p along x has to be greater than or equal to h on 2. So that's the way your book writes it. And so we'll go ahead and stick with your book's version of this uncertainty principle. Your book discusses all the fact that there's various factors of pi that you might need to absorb and additional factors of 2. But we'll just use this as a nice estimate for the minimum uncertainty. All right, so that's the general form. And I've written here a subscript x on the p because, in fact, this is true in every direction. So in the y direction, I have another one of these. And similarly, in the z direction, I have another one of these. Okay. Now, I'll summarize, because I don't want to keep writing three things. I'll just write this as delta, and I'll just say I, and delta pi greater than or equal to h on 2. And then I mean by I, that takes x, y, z. Those are those different values. So that I can talk about one equation rather than three. Okay, so looking at that equation, well, delta pi, the momentum or the ith component of the momentum, and really the uncertainty in the ith component of the momentum, well, that thing is just going to be the uncertainty in the mass times velocity, where the velocity is in this ith direction. So the uncertainty in that would be the uncertainty in mass, but there is none. And the uncertainty, sorry, that's a v. Uncertainty vi. Okay. What about delta I? Well, for this problem, it's actually really simple. I'm talking about a cube, so all the sides are the same, and I'm trying to put this particle in that cube. And I don't know if it's sitting down here, or sitting up here, or sitting here, or back there, or in this corner, this corner, this corner, or of course anywhere in between. But if I can range sort of along x from anywhere to here, here to here, between here and here, then that's got an uncertainty of L. I can range between here and here, that's an uncertainty of L, and along this dimension, an uncertainty in L. So the delta i's are all equal to L. Okay, and that's only true because it's a cube. If this were a rectangle or some other shape, right, some sort of nice, well, rectangular prism, the height of the prism is also different to the dimensions of the rectangular base, then each delta I would be different. But since I've got a cubical box, all the delta i's are the same. So I can just write it like that. And then I can come back and look at my equation. And that equation in the box turns into just the fact that L times m times delta vi has to be greater than or equal to h on 2. Now, we want something about the velocities, and delta vi. I'm just going to say equals as I rearrange. because I'm looking for the smallest range of values, and if I have to be greater than or equal to something, well then the smallest I can be is to be equal to it. So I can take my delta VI to just be h onto Lm. Right? L is the side length of the box, that's the 10 to the negative 14th. M is the mass of the proton, and h is Planck's constant. Now that's all well and good. That's the uncertainty in each component of velocity. So I have to form the overall velocity. Well, delta V is actually the square root of the delta VI. So delta Vx squared plus delta Vy squared plus delta Vz squared. And that's just coming from essentially Pythagorean theorem applied to the fact that I'm moving with some Vx and some Vy. If I want to add those two, well, I know that I can do that because I can just call that A, that B, and that C. And that certainly works. C squared is B squared plus A squared. And then I just have one more dimension, so I just draw this again, and that's where the last part gets added as well. And so, indeed, that's what I need to do. Now, these are all the same. They're just h onto Lm. I've got 3 of them. I end up with a factor of square root of 3, h to Lm, okay, for delta V. And so that gives me the smallest range of values if I do one more step. Okay, and first, before we form a range, what we need to know is exactly what does this thing equal. So we need to go ahead and put in some numbers, some numerical values for h, for m, and for L. So L is given in the problem. The mass of a proton as something that you may or may not remember, but it's certainly something you can look up. So your book has a nice table of a bunch of constants if you don't happen to have them memorized. And that's also where you can find in that table the value of h if you don't happen to have it memorized. So the value of h in SI units is 6.64 times 10 to the negative 34 joules per second. The value of the mass of a proton is 1.67 times 10 to the negative 27th kilograms. And so if you put that in, then delta V ends up equaling 3.4 times 10 to the 7th meters per second. Okay, and if you turn that into something about the speed of light, well, it turns out that that happens to be about 1/10 the speed of light, a little bit more than 1/10. And if you want to make this properly into the range, well, you assume that it's centered about 0. So that means that V, if this is the width of its range, then V has to be between, oops. So then V has to be between, there we go, basically delta V on 2 and negative delta V on 2. So that's 1.7 times 10 to the 7th meters per second is less than V is less than, and that's with a negative sign, and the same thing on the right. So that's the smallest range that it can have. And equivalently, if you want it in terms of C, well then it's 0.055 C. I know, 55 C. Okay, so that gives us the smallest range of values that it is possible for a proton to have and still be properly confined in this box.